I'm Mark Wensler, the head of the Chautauqua Climate Change Initiative. And it's my pleasure to introduce this morning's speaker, Mike Humphrey from the Buffalo Astronomical Association. Was anybody here last summer when Mike gave a talk during our Star Party event? A couple people, yeah. So we had a terrific dark sky star party last summer, and Mike gave an excellent talk and helped us, and they brought their telescopes from Buffalo. We're not doing that this summer, but we are going to do it again next summer. So with that, I want to introduce Mike Humphrey. Mike was brought up on NASA and the Mercury through Apollo programs, which served to fuel his interest in science. He loves outreach and works hard to provide audiences with the most informative and entertaining event he can, and you'll see that this morning. He joined the Buffalo Astronomical Association in 2010 and was the editor of the newsletter from 2014 to 2019. In 2017, he was given an Achievement Award from the BAA College of Fellows for his work in outreach and developing a partnership with NASA's Night Sky Network. Mike then served as vice president and was elected president in 2018, position he currently holds. Additionally, Mike was appointed chairman of the Northeast Division of the Astronomical League and sits on the board of the Buffalo Audubon Society. He volunteers as a NASA partner eclipse ambassador, promoting public education for the upcoming eclipses, which you'll hear about, I think, and promoting public education so they can be viewed in a safe and awe-inspiring manner. Mike is happy to be back at Chautauqua, as he and his family have spent multiple summers visiting here. He has a special connection to the institution, as his daughter participated in the summer intensive dance program and later returned as an instructor under Jean-Pierre Monifaux. Without further ado, Mike, welcome.
Hi, thank you. Thank you. And for those of you who saw me before, nice to see you again. For those who haven't, it's great to see you. Just want to tell you a little bit about my group. It's BAA. We're all volunteer. It's 150 people, and we do talks and things like this all the time, because we like to go out, talk to people about science, and let people know what's going on in the night sky. And I'm going to switch this over for just a second, which is that. Why are we doing this? I'm the type of person, when I walk outside, I take a look up in the sky, and you see a bunch of blobs, but I see more than blobs. I see history, I see the future. I see stars that have led people for millennia, and stars that will continue to lead people in the future. Stars, the stories to tell. Astronomers are the tellers of the tale. That's what I do. It's great to see everyone, and I'm going to go ahead and we have chapters. Now, we look at telescopes. We have a couple of space-based telescopes, and some of these names are probably familiar to you. Hubble, maybe Spitzer, Chandra. They look in different wavelengths of light. And when we talk about the electromagnetic spectrum, and we're going to jump right into everything, we're only looking at a small piece of it when we look at visual light. So right now we're using the visual spectrum, but there's so much more to the story. There's so much more that we can do. So many other things that we can see. And when we look at the study, why do we study light? And why do we study specifically infrared light? I think right now we're looking at a couple of pictures of some meerkats and a crocodile. Oh, I'm sorry. Can you hear me now? How about now? Okay. Okay. Here's a picture of some meerkats. Okay, we're looking at them in visible light, and we're taking that little piece of the spectrum and taking a look at the meerkats and taking a look at a crocodile. Visually, we can see certain information, but when we go to infrared, oops, went backwards, and we're gonna go forward. We have so much more. And now the crocodile that kind of blended into the background is very apparent. So are the meerkats, which kind of showed around, but now we can see even more, and we can learn more too. We're looking at the meerkats, which are throwing out a lot of infrared light. Same thing happens with the galaxies. Now, when galaxies are very, very far away, the light comes through in the visual spectrum, but the further away it is, the longer light has to travel. The longer it travels, it begins to stretch. As it begins to stretch, it shifts out of the visual spectrum and shifts into infrared. When it shifts into infrared, we can't see it because it's invisible to us. So now we need a way to detect that light because it's going to give us the next chapter in that story. Now, key thing here, we're not looking for heat. Sometimes you hear that is that we're using the satellites and we're using our platforms to look for heat. We are not. We're looking for infrared radiation. This gives you an example. As you can see here, you can see the Webb is on one side and it shows you the galaxy, ultraviolet. It shifts through our visible light spectrum, goes infrared. That's where Webb lives. That's where it sits. That's the thing that it likes to do. Look for the infrared light. Essentially, what we're doing is creating a cosmic flip book. This is the best way to describe it. The further away something is, the further away that light is, if we pick that light up, we can see as those galaxies progress. And it shows us what our past is. In a way, looking at our past can also tell us our future. And talk just a little bit about the telescope itself. Webb is remarkable. And the fact that very different from a lot of the probes we have, especially, and those of you who remember what happened with Hubble, Hubble was launched. We had a lot of high expectations for Hubble. When it got out in space, it was horrible, and we have a whole talk on exactly what happened. But essentially, Hubble had astigmatism. They were able to correct it with a corrective lens. That's what they did. They put a contact lens on it. We can't do that when it comes to Webb, because the Webb is significantly farther away. Hubble was about 200 miles away from us, 200 to 300 miles. The Webb lives at a point that's about 1 million miles away. So servicing is going to be very difficult, if not impossible. This is the most distinctive thing about it. Remember, we have something that's large. We've always launched platforms and very small platforms. This is a person standing next to the Hubble mirror, which is just a little under 8 feet. Right next to that, you can see the Webb mirror, which is just a little over 21 feet. So imagine getting something that's 21 feet into orbit, plus all of the other things that are involved in that. We're going to take a look at this real quick too. Hubble have several cameras, but on the Webb, we have some very specialized camera. These are 4 cameras that are listed, but there's actually 5. The near spec, the near cam, and the nearest, which actually go just a little bit in the visual spectrum, and then they go into the near infrared. And then the last one, the MIRI, which sits in the mid-infrared range. And if you try and say that a couple of times, it'll be really, really difficult. It's a great tongue twister for you. Absolutely. Now, this is how the Webb has its camera set up. When we set it up, it's for a field of view, and this is how the field of view looks. Now, you notice on the left-hand side, near cam, there's 2 of them. And they're set side by side, and there's a space that's right in the middle. This is going to become very important later, so remember that for the test. You all can see where NIRI and MIRI and the near miss and the spectrophotometers are. Everything is located, and this is their fields of view. And in this case, we're looking at a whirlpool galaxy. We can see what the field of view would look like. There are some reasons for this because we had to develop something that had as many cameras and as many detectors, plus with a large mirror, so we'd be able to see those things and be able to put it in a small enough package to get it into Earth, and everything would work without bothering anything else. Another thing that's very distinctive is the sun shield. Now, this is 2 views, one on the top, the observing side, which is where the mirror lives, and behind the mirror, there's the science package. The other one is on the bottom. Now, on the bottom, you see a square box, and that box is where maneuvering, navigation, everything takes place. Now, the sun shield provides 2 specific types of, does 2 specific jobs. The first is to protect the satellite itself and the platform itself from heat, and we'll see that in just a few minutes. But the second thing is it's got to maneuver, and in maneuvering, it uses rockets, it uses fuel, and that can cause contamination to the science platform. The sun shield helps prevent some of that contamination by keeping that away from anything that's related to detectors. Also, any heat that's from using the rockets shouldn't go to the detector. So everything that we're seeing, that heat will create infrared radiation. And remember, we want to see things that are in space, not things that we know. Also, the sun shield is designed, and again, we'll see that in a few minutes, that is designed so that it's facing our sun and it's facing the earth and it's facing the moon and anything else that would generate any type of infrared signature. So it doesn't have that infrared signature that's going to interfere with its observations. When James Webb was launched, it took 30 days for it to get to its station keeping point, which is called a Lagrange point, which is just about 1,000,000 miles from Earth. Now, the Lagrange point, or the L2, is a point where we have equilibrium. So the gravitational forces of the sun and the gravitational forces of the Earth acting on this James Webb, pulling it in, are counteracted by the centrifugal forces pulling it out. Essentially, we create a very stable orbit. There are 5 Lagrange points. L2 for what we want is located outside of the system. L1 is actually located between the Earth and the sun. And then there's L3 and 4. One is located in our orbit in front of the Earth, one is behind. The one that we use is L2 because we're able to look out and eliminate some of the internal forces that we have here from bothering our observations. Once it gets to its L2 point, what it does is it goes into a halo orbit. And in this case, you can see the Earth, the moon, and the sun, and the positioning of the Webb. Now, as the Webb goes into its L2 orbit, it just sits there. We can keep it in station keeping, and we only have to do minor course corrections probably every month or so. It has a 5-year mission, so it's a 5-year lifespan, but has enough fuel for 10 years. Part of that's because NASA has gotten very, very good at building things. You've seen some of the Parker solar probes. You've seen what's happening with Opportunity, Spirit. Some of these other probes, they tend to last longer than their lifespan, sometimes going several years. We want the same thing to happen with James Webb. James Webb also has a refueling port because it's so far away. We don't know how to refuel it yet, but we put a port on there just so when time comes, we can have a robotic mission and use that port to refuel it. That's how NASA is thinking ahead. I thought that's a great idea. Always plan ahead. We think it's going to go for a long time because it's been very, very successful. And actually, I want to just jump back here 1 second. I did want to point this out. One of the things that we have in engineering is we call single point failure. Single point failure is a concept where if one single point fails in an operation, the entire operation is gone. Hubble had several. In the case of Webb, there's 344 single point failures that we were looking at. And you keep an eye on because if it had any one of those 344 single point failures, the mission would have had to be scrubbed. And in this case, it didn't have any. It went right through, went right to its orbit, got ready to rock and roll, a full robotic mission. The other thing about Webb to understand is we can send the information, but it takes a couple minutes to get there. So a lot of things it has to do by itself. So it is a robotic mission. We say, this is what we want you to do, and then it does it. So we're sending commands, but it's really processing a lot of those things by itself. I did want to bring this slide up because I love this slide. If you go on, and this is an easy site to remember, just type in where's Webb. You want to know where it is? Where's Webb? Type it in. It's going to take you right to this location. A lot of the images and the information I get is gotten from this site and from other NASA briefings that I've been to, but I really enjoy this site for a couple things. First off, along the bottom, it tells you what Webb is up to right now. Now, this I took a couple days ago. Along the top, it tells you what temperatures it's looking at. Now, for all the science geeks out there, absolute zero is minus 273 degrees. If you look on here, you'll see one of the, on the right-hand side, one of the detectors is minus 267 degrees centigrade. So 3 degrees away from absolute zero. At the same time, if you look on the far left, you'll see the sunshine has a temperature of 50 degrees centigrade. Now, let's put this into Fahrenheit. On the sun side, try and say that a couple times. We are seeing a temperature of 122 degrees Fahrenheit And on the cold side, we're seeing a temperature of minus 444 degrees centigrade. I mean, Fahrenheit, sorry. Now, when you look at that temperature, you look at the sun shield. At the maximum distance of each sun shield is about 10 inches. So between 40 inches, we have that temperature differential. I think that's pretty cool. I also wanted to mention about a couple of things to think about. The sun shield, believe it or not, has holes in it. And these, if you've seen anything, Mylar, camping tents, sometimes we'll put a small hole in it. And what that does is if a micrometeorite hits it, that acts as a stop. Because what it'll do is if it starts to rip, it'll get to that hole and stop. These holes are set in areas so none of the holes overlap. The other thing is if you look at the mirror itself, the mirror has 18 mirrors. Each mirror is independently controlled, focused, and we can also flex it. So if something hits a mirror, which it did, a micrometeorite did hit one of the mirrors, made a small hole in it, they're able to reflex the mirror so they can refocus it and take that little anomaly out of the range. And come by computer, we can also do that. So as far as doing a lot of things, there's been a lot of thought behind this to really make it work. But when people go by, there's a lot of thought behind some of the things, and a lot of people are looking at it. In fact, it's been a worldwide collaboration. These are the countries. The United States is what we call the primary investigator, and in Goldstone, California, that's where we have our primary location to bring the data down, and then it's distributed. But as a primary investigator just means that we're in charge of the program. But these are the countries that have a stake, that have helped, that have done some of the engineering. And now that it's up, these are the international partnerships of people who are using the web, that are putting together proposals, doing investigating. A lot of the information you see now, just so everybody knows, stuff coming down from the web, you can go and take a look at it. You can download yourself. You can manipulate it. You can do things you want. It's public knowledge because we did pay for that. So we own that. And I like to point that out because people say, oh, no, I can't do anything. Yes, you can. You can see the raw data and you can go into their website. Some data does get held for 24 to 48 hours. Some, depending on the investigator, may be held a little longer. But all the data coming from Webb, such as Hubble, Spitzer, Chandra, Parker Solar Probe, all of that data from any of the NASA probes is all public knowledge. It's all publicly available, and you can go to the site, you can pick it up, and you can take a look at the raw data when you like. So we've talked about the web, we've talked about the platform. Let's see what it's been up to. Remember, we have a 5-year mission. So we're only going to talk about the first 2 years, because that's all it's been up. This is one of the first images that came through. There's a series of 5, but because of the talk and I wanted to get a lot of stuff in, I had to take some of them out, but I just wanted to bring this one up. This is Carina Nebula. I'm going to zoom in on this just a little bit. And you can see the areas that are outlined. These are star forming regions. And you see some of those dots. What Hubble does is Hubble can take some pictures, but the nebula and the cloudness of the nebula, the clouds and the smoke kind of get in the way. What Webb does is it looks in infrared range, which is visible, but the clouds become invisible. So when we're looking into a nebular region, planetary, or looking at the solar nebula, we can see through that region, we can see the things behind it. And in this case, you can see several star forming region. In fact, several stars, so protostars being formed. Yes. No. And actually, I was going to mention this later, I'll mention it now. Some of the images that you see now, we know infrared and we've seen that it looks red. And that was clearly the expectation from a lot of us. You know, these are going to be cool, but they're all going to just be red. What they have done is they shoot, quick lesson. When you watch TV and you're watching color TV, you're actually watching multiple guns shooting multiple colors, and that gets mixed by your brain. When you see color photographs, it's the same thing. They shoot through multiple layers or different layers of different colors. And by using the different tones, they can get you a color without getting really too dramatic. What they do with Webb is they'll shoot an image and they shoot it through different filters. Then they take those filters and they stack them on each other. And when they stack those filters, they get the color. Effectively, what they've done is they've taken the color spectrum and they shifted it down into the infrared range. So the colors you see here are typically the colors that you would see if you were right on top of this. Yeah, they try, there's a concept which is false color. Sometimes that's done to enhance a region, but they're not really doing that in this case. When you download the raw data, you usually get several files, and each file will tell you which filter it was shot through. And when you process it, if it was shot through a red filter, then I'll process it through a red filter. I'll stack that onto a blue filter, into a yellow filter, and then I'll get the colors. Everybody recognizes this? Real easy. Now, the Webb is not going to take pictures of Earth, Sun, Moon, Venus. The reason is because they're on the inside of our solar system, and facing the sun, what'll happen is it is so sensitive that the sun can burn out the detectors. So you're not going to see those. But when we go to the outer planets, and let's take a look at Jupiter, something amazing comes up. Now you see the great red spot isn't red. It's throwing off a lot of infrared radiation, so it changes color. Also on the bands, but you see the polar caps, and you'll see something here in this next slide. There's a ring. The upper and lower image, that's halation that's caused by it being so bright. So you see the little lines on the bottom, they sort of don't care because you can see the actual striations that are coming off from the polar caps, but you see one moon and you can see a ring. And again, this ring is visible in infrared because the amount of infrared radiation is throwing out, and it really isn't that visible in, well, I don't want to say it's completely invisible, but I will say that it's extremely, extremely hard to see if you're trying to find it in our natural spectrum. Let's take a look at something else. Here's a ring planet. Now, this one is not Saturn, and we know that because it's on its side. And there's only one planet, which is Uranus, that floats on its side. When you see Uranus, you won't see these rings. Okay, they're very, very small, but excuse me? When you see it, it's very small. I'm going to turn this just a little bit this way. It's very difficult to see, but when we set it up this way, they throw off a lot of infrared. So now you can see it with the bands. I don't know. That help? I think that's worse. Let me. How's that? I'll try and speak closer to the mic. Sometimes you get a lot of reverberation here, so I don't want to blow everybody out. Okay, so now we're looking at Uranus. You can see the bright polar spot. It looks like a big bubble, doesn't it? Because that's the amount of infrared that is throwing out. Remember, this is a cloudy planet. You can also see the different rings that are located within the bands around the planet. Okay, we're looking at Neptune. Now, this one was shot in 1989 by Voyager on one of its close passes. This next one, this was shot in Hubble in 2021. This yeah, isn't it cool? So again, we have another ring planet. Now we expected to see this because a lot of our larger planets do have, they have orbitals and they do have rings, and there's a lot of dirt and things still out in the universe. So we expected to see this, but this has been kind of a surprise that the amount that we're seeing. And again, this is because you're looking at a cloudy planet, but you can see some storms, which is the really high areas, which are throwing off a lot of infrared. And you can also see a couple of moons. This one's kind of interesting because we also use the Webb to look for exoplanets. Now, the way we look for exoplanets is you find a star, you keep an eye on it, and you wait for the luminance to drop. And you keep an eye on how when the luminance drops, and when it goes back up, you know something, essentially we call it eclipse or a cold hit it, or something just moved in front of it. Then we can do some calculations, and that's actually better in this picture. So in this one, you can see we do an average range. It shows us what the dip is, and then there's some calculations to figure out how far, how large, and what the orbital period of an exoplanet is. And so now we're seeing more exoplanets because we're much more sensitive to the amount of drop that you see in something that's further away. Okay, this is Hubble. Hubble shot this. This is the Phantom Galaxy. Hubble shot this optically. There's the Webb. Webb is taking a look through it, and this one I like because it's a great example of how the Webb is able to go through the gaseous part of nebulous and be able to see beyond that, so we can see things that we normally wouldn't see. Now, I've been asked, is the Webb replacing the Hubble? No, because the Hubble really looks into the visible spectrum. So what we do is we're using the Hubble and we're using the Webb at the same time for images like that. Gives us different ways to look at things. We can set up the formal regions. We can take a look at stuff and further analysis by using all of our telescopes at the same time. This one is Fomalhaut. It's a star. Now, in the past, we've seen this star and we knew that it had one outer band, but Webb has been able to show us some of these inner bands. Now, two things about this photograph. Number one, the little black spot in the middle is not a rock, it's not anything, it's actually oversaturation from the star itself. And it caused that to happen. I mean, that's something that they can do some work with, but this is the initial that came out. The second thing is you will notice that there's an outer band, then there's some inner bands. We suspect that these bands are asteroid belts being carved out by some exoplanets, much the same way that the exoplanets, in this case, we have, and everybody knows that we have an asteroid belt between Mars and Jupiter, and we also have one that extends beyond the range where Pluto is. So something very similar is going on here. One, there we go. This is a tarantula nebula. Now, tarantula. It's called tarantula because it's got a lot of tendrils. When you see the entire nebula, there's a lot of tendrils that go all over the place. And somebody thought it was a cool name. If you see it first, you get to name it. I'm waiting to find something I can name. Now, right in the center, you'll see a bright star that's got a couple spikes on it. But right next to that, to the right, you see a little star forming region. This gives you an idea. This is that same region looking in the visual spectrum. In the visual spectrum, the smoke, the smoke and the nebula is hiding these other stars. Oh, let me get back there. There we go. So if you look at the two, between the two, in one case, you can see a lot of stars in the background, and the second one you can't, and that's because of the infrared, and we're able to pierce through. Now, this one is a kind of a rare star. We found about 600 of them. It's called a Wolf Raylet. Now, Wolf Raylets are very short period stars, as you usually see something just before it goes supernova. Now, a couple of things happen when a star goes supernova, and one of those things is it begins to shed its outer layer. As it sheds its outer layer, this will happen. This is something that is very, very rare to see because it's so short-lived. Also, because most of this radiation is coming out in infrared, it's very difficult to see. Optically, you wouldn't see this. The only way we can see this is with the Webb and looking out through a variable star field and doing a survey, you would find some of these. In this case, excuse me? I don't want to say a couple months. I mean, maybe weeks, maybe even less than that. In some cases, even smaller. Now, this is going out like rivulets though. Like if you take a, let's say you put a pebble into a pond and then you get the concentric circles going out, very much like that. But it's happening at a speed that's very fast. So sometimes it's very difficult to see. And we know they're short-lived because sometimes we can, sometimes we can't. We're just really getting into the research on them. So hopefully we'll have some better answers at some point. It's just one time you see it and the next time you don't, but now we can see it. This, let's see, is another Wolf Raylet. Now in this case, the nova is actually lighting up the nebula. And we can see how it's being lit up from the infrared radiation that's being thrown out from the nebula. Does everybody remember this? Who remembers it? Just shaking. Okay, Pillars of Creation. Pillars of Creation under Hubble. Pillars of Creation under Webb. piercing right through. We're seeing all the star forming regions, but now not only do we see the star forming regions, but we can see the stars being formed. This is Spitzer. Spitzer is a far infrared, and this one that was launched in the 90s. And Spitzer was designed to look in the same range, but a little bit deeper down. This is Hub. This is Webb. Sorry. Same location, same area. I wanted to bring this one up because I had this one up when we first started and we were talking about stars and everything. I decided to go out and count how many stars are in this picture. Yes, because there's just about 20 stars, the rest are galaxies. Trick question. We can tell the stars. The one that's in the upper part, you can see it's got a lot of diffraction spikes. When you see Webb pictures, they'll have these very characteristic diffraction spikes, which is caused by the mirrors themselves. Usually the stars will have these diffraction spikes, but the galaxies don't. And there's a lot of reasons for that. We can actually get into that, but then you guys will be looking at me like I'm crazy. But if you look here, you'll see several galaxies. There's a spiral, there's some flat galaxies, there's all sorts of things in this image. Here's Spitzer again. This is Hubble. And that's Webb. Now this next one. This is a protostar. This one we found, and we've looked at a couple star forming regions. We looked at some supernovas, but let's take a look at what happens when you form a star. So in this case, hopefully it's very apparent here. It's kind of a flashlight shaped. And if you take a little close, you'll see right in the middle is this tiny black band of material. And it's kind of stretching it out. What's happening is there's a protostar here that's pulling in material from nebula and it's lighting it up as the star begins to go through its formation period. What will happen is as it pulls enough material and it gets large enough, it'll ignite, start fusion, and it'll glow like a sun. That little black band is probably the size of our solar system. That's a protodisk. Protoplanetary disk will eventually congeal and it can form planets. This is Hubble. Now, this is an intergalactic collision. These are two galaxies colliding. When they collide, the gravity starts to intermix and then they start to do all sorts of fun stuff. And it looks like that. There's a lot of stuff going on up there, isn't there? I did want to bring this up. Webb has a couple spectrophotometers on board. And those spectrophotometers allow us to break up that light. So we can process the light, and based on the breakup, we can find different elements and see how those elements are created and what they look like. And this from the near cam and then from the nearest, we're able to see water, CO2, carbon, based on the atmosphere of looking, in the case this is WASP, it's an exoplanet WASP 39b. So yeah, we use the same kind of Star Trek thing where everything has got a name and a number. This is kind of interesting. Now, remember what I talked about the near cam? This is a near cam image. Well, what they do is sometimes it's very valuable to take a picture of an entire star field. But what do you do when you have a really, really bright star in that star field? Well, if in the case of formula, if you take it, you're going to get it overexposed, oversaturated, you got a problem. But you can take that slit and that spacing on the near cam and put that spacing over the bright star. And when you do that, you get this. There's two cameras, and the split is between camera 1 and camera 2, but we use the two cameras to shoot one star field. Right, and you can kind of see it just on the edge. This is kind of interesting. It looks like somebody made a mistake, because if you look on the right-hand side, you see a star and then you see a bunch of anomalies all over it. That's actually gravitational lensing. Now, gravitational lensing is caused when you have something, and it's usually either a bright star or a huge galaxy with a lot of gravity. The light comes through, as it's going through, it'll be affected by whatever that object is in the front, and that'll bend that light, just like a lens. What you're seeing here, and again, looking at the star, there's a triangular shape and then a couple striations around there. Those are galaxies several light years away from our main star. And the gravitational lensing is just making that happen. This right here is actually a better shot of that. You can see we focused in, and on the top, you can see just a little arc-shaped piece with a tiny red dot, and on the bottom, you see tiny red dot. This is the same thing as gravitational lensing. But now what happens, because all these are edge on, but what happens if you see one and it's a perfect alignment to the star and to our platform? You get an Einstein ring. Now, this one is about 12 billion light years. So these two lined up, and the one that's around the ring is about 12 billion light years away from us. This is kind of interesting. Hubble did a deep sky survey, and this is the Hubble deep sky survey. This is Webb doing that same deep sky survey. They look almost identical, except for one thing. Hubble took 11 days. Webb took less than a day for the same image. This one I wanted to bring because this is brand new. This one just came out about 4 or 5 days ago. Orion Nebula, which is in, if you go up and you find the Orion constellation, the Orion Nebula is there. This is called the Orion Bar. What we did is we took Orion Bar and then focused on it, on this region, and went a little deeper. Now we see a star with a protoplanetary disk. This is the stuff that James Webb has been doing. And this has only been a 1.5 years, and the mission is 5 years. Something to think about. I want to thank you, but before I go, one more thing. Save the date. April 8th, total eclipse. Now, this is what we call a cheap solar eclipse because you don't have to go anywhere because it's here. So you don't need to spend, you don't need to go on safari, you don't need to go to a tundra region, you don't need to get on a boat, you don't need to go to a foreign country, you can just go outside, look up, and you'll be able to see it. California, they can come here. But it's because it's here and because it's over the United States, you don't need to travel, you don't need to find hotels unless you're from California. You do need to be able to travel here. I can tell you right now, I've gotten calls from different parts of the world, from different astronomers who want to come here. They like us for some reason, you know. I do know I've talked to people in Canada, the Royal Observatory, and there's some people from Royal Observatory who will be coming here. So we're coordinating with Borders Security and a lot of other people to try and get visitors in so people can enjoy the eclipse. In our cases, it's going to be great for us because we're just going to go outside, look up and say, hey, wow, that's going to be great. This is the path. And all the images and everything I've used today, I got from NASA, from the website. The third one, Buffalo Astronomy, that's our website, which is the BAA, which is my group. As I said, it's all volunteer, everybody, and we're happy to help you with things. Buffalo Eclipse is another one, also very easy to remember. Buffalo Eclipse will give you more information about the eclipse, and as we hear more of viewing locations, we'll have that for you. And that last one, info@buffaloastronomy.com, that's also our website. Now, if you have a question, send it to buffaloastronomy.com, that info. And 9 times out of 10, I will probably be the person answering it. So thank you very much. Okay.
So we're going to start our Q&A period. If you have a question, please step up to this microphone and ask your question. I want to thank Mike. I want to also ask Bob to come up and say a few things, our president. And I want to announce next week, Dr. Susan Woods, a dermatologist, is going to talk about platelet-rich plasma for wound healing and cosmetic issues. She's doing some really interesting work And I think you'll appreciate hearing her speak. So come back and see us again next week. We will let Bob, I have to let our president say something or he'll fire me. So. Bob.
We've been doing this for 20 years. We've been doing it concentratingly for 5 years. And I want to thank all of you who've been supporting us and been happy to have as much science as possible at Chautauqua. Some practical things we have done. For 5 years, we've given a scholarship to a student voted at the Chautauqua Lake Central School as showing the most positive interest in science to help them go on to pay for school. We can't give a lot, but we're giving $500 a year to a student, which they appreciate. We also, believe it or not, it costs us about $500-600 to keep our website up every year. So we need help for that. And then we're really so grateful to the Hurlbut Sanctuary for letting us do our talks here. And to show how much we appreciate it, we give them a love donation at the end of the year. So altogether, to keep doing this, and we're not a membership organization, we have no dues, we're volunteers. We need to collect about $1,500 a year to pay those 3 essential things. There's a little basket in the back. Just put your Ben Franklins and your whatever in there, and we'll be also, you will be able to see with great detail in a couple of weeks. We will post this talk on our website with the images. But thank you for coming. Thank Mark for helping us find some wonderful speakers that support the Climate and Lake Initiative. Thanks to the Chautauqua Daily and Maria for writing a nice story. Your presence here shows the power of the Chautauqua Daily. Thank you for coming.
How do you know a given image is not an artifact?
Well, what you mean artifact is something that might be on the lens or something like that, or?
For example, with medical imaging, which I am part of, you can get artifacts that is not a real image. It's an image created that is not existing in reality.
Okay,
And so you must have ways to tell what's, like you pointed out, some things maybe, I call them artifacts, but you call them whatever. What do you do to determine what's real and what's maybe artifact from the technology?
there's a couple different ways. For instance, in the Jupiter picture, when I said that the polar caps were showing off a certain amount of halation. So those are things that you would know and you expect. Some of the other things, we take multiple images of different things, and by looking at those multiple images, you see if something appears in one image and if it doesn't appear in another. And you can also, there's different catalogs. For instance, if you look at and I call it catalogs. So let's say we do an image and we're doing an image from Hubble, and then we do an image in Webb, and then we see something we don't recognize. We can go back and forth and do a comparison. And sometimes that'll tell us when we're seeing something that's real or something that's problematic. A lot of work has been done to try and keep a lot of the halation and a lot of the problems out of the equipment itself. And we're always doing more. And when I say we, it's people like me and other astronomers. We give feedback and we talk to NASA and say, okay, we've seen this. And then people can look at things. So it's a give and take.
Born short.
Okay, I can hear you.
More of a request than a question. I thought it might be interesting for the group to know who was James Webb and why is this telescope named after him?
Oh,
Ancillary question, who were the team that put this together?
but this,
No, the telescope. Who built it?
oh, okay. James Webb was a NASA administrator. He did a lot of work and actually promoting a lot of the programs. That's the very, very short answer. But because of the work that he did, and there's a lot of things about him, but he tried to really promote a lot of the types of projects that are going on now. And they look for different people, such as Hubble was named after an astronomer. And a lot of times we try and name after somebody to just honor them for the work that they did. This was put together. And again, when I showed the one slide that says it's a collaboration between countries, it was a collaboration. People from all over the world came to put this together. The US is the primary principal investigator, and we were the primary contractor, so we were in charge of it. But different parts were different by different people. So it came from everywhere, from all over the place. Yes.
Hi, can you give an example, if there is one, of something that Webb has found that's wholly new or has totally changed the way people, our scientists are thinking about the universe, or sent things in a totally different direction?
Oh, actually, two things. One is the Wolf-Rayet stars. Oh, yes. Can you give an example of something that the Webb has seen that has changed or affected the way we look at the universe? Two things. One we talked about, which is the Wolf-Rayets. By looking at the Wolf-Rayets now, we can actually work on them. And because they're so short-lived, it gives us a way to really start examining and start looking at those. So some of these things were really in theory, like an Einstein ring was a theory, but now we can see it. The Einstein ring also showed, I think it's like 12 billion light years away, I think was the last thing. So we're able to see things further away. Also, because of the amount of time and the way it's so sensitive, we can scan more and do more work in less time. Yes.
Interesting conversation around galaxies colliding. That means there's nothing stable in space.
Correct.
That galaxies are moving.
Everything is moving.
So with that being the case, obviously it's sourced by gravitational pull somewhere.
Yes.
And do we know at what speed the movement occurs? And is there some central place for gravitational pull that's moving everything to a central point?
We know the speed. Okay. Our galaxy, the Milky Way, is on a collision course with our closest galaxy, which would be Andromeda, which is 2.5 million light years away. So mark your calendars in 2.5 million years. And we know how fast it's moving, and that's what we think it's going to take about 2.5 million. But things are not moving around a central point because we haven't found that central point yet. Because everything is, the best way to describe it is moving around like swirling. So it's very difficult to find one spot where everything is moving towards or moving away from. We do know that the gravity of different objects like a galaxy will affect another galaxy, and those galaxies can start pulling together. Sometimes they just move between each other because we've seen that. Sometimes you have a galactic collision where the gravity of those two will intermingle and just different things will happen, which is what's great on the Webb because we can see those because those things have happened in the past. And we can see those now because we can see things from the past because we're seeing, say, 12 to 15 billion light years or 12 to 15 billion years ago. So yeah, it's giving us some information on things, but we see a lot of swirling. So we don't have a central location yet. We just know that things are happening.
I just wanted to add to your commentary about James Webb.
Yes,
He was the NASA administrator during the Apollo program.
yes.
So he sent 12 humans to land on the moon. So it was very fitting, I think, for NASA to name this after him as again, we go into the unknown. So I just wanted to give him that shot.
I remember during the Apollo missions, Gemini going all the way back to Mercury and some of the things that are coming out now. I mean, there's a lot of work and a lot of things that happen that people don't know about. And it's good that people know about some of those things. One was Hidden Figures, let you know some of the people who worked behind the scenes. And it's very important that people understand our history.
And now we have Artemis.
Artemis is on the way.
A few minutes ago, you answered the question of what do we know about the universe because of this that we didn't know before? And I have a follow-up question to that. What are some of the things we want to know about the universe that some of the years of Webb might reveal?
One of the things, and again, this is looking into the past. We can, and I put up a slide and it said about the cosmic flip book. When we talk about the flip book, we want to see what happened before. We can look at galaxies just like ours, and we can see how those galaxies were formed, which direction they're going, and how those galaxies, what happens as they move forward, as they end. Okay, we know our sun at some point is going to run out of fusion. Okay, and then it's going to become a red giant. We know some of these things already. So what happens when that happens? So we can find someplace else that's very similar, and we can see how that process occurs. We can also see what happens looking for exoplanets if we need to leave here. Because, you know, if we know our star is going to explode, you know, it's a good idea to start planning for the future. Again, 6-7 million years seems like a long time, but, you know, let's start talking about it. The big thing is we can see, this is where we are, this is where we are. These are the things that are happening. So now we can see them. And we can say, okay, well, I see this galaxy that's similar to the Milky Way. An edge-on spiral galaxy is going through these processes. We will probably go through the same type of process. When you look at our galaxy and you look at how big the sun is and where we are in this galaxy, we're actually, when you've seen the Milky Way pictures and you see a really big thing in the middle, that's not us. We're way off in the corner. It's a very tiny speck. And there's so much thing happen when you see how many galaxies are out there. There's so many things going on. There's new discoveries. There's, I think it's methane, carbon methane is a new element that we discovered by looking out there. And so we're seeing all these new things. Helium-3 is something that we found on the moon. So how can we use helium-3? It's answering questions. And that's what we want to do, is we want to answer some of those questions. Those questions lead to more questions, and eventually we'll get some really good answers that are going to help us as we move forward. Oh. Science matters, I like that.
A few months ago in Sky and Telescope, there been a short article about some, not Hubble, Webb pictures that had just come back of the very distant future, very distant past, as close as they could get to the Big Bang. And the article talked about, they discovered that there were far too many galaxies, they were far too bright, and the redshift was way too high. Anything about that since then? And I think this was May or April.
Well, there's going to be, actually, one of the pictures I showed, which was the Einstein ring, shows you a very distant galaxy, which are things that we're seeing. A lot of times we're finding a lot of this information. One of the reasons in the amateur astronomy, what we're finding is there's so much data coming in that we're helping NASA and the groups out because they have so much stuff to look at, and it's very difficult. These new satellites, I mean, again, less than a day to get this data, and the data comes in and there's just so much, and you've just got to get people looking at it and trying to figure things out. That's what's difficult. Everything brings new things, and every day we get more stuff. Every day more light from distant galaxies hit us. There's galaxies now that we see today that we never saw, say, 20 years ago, because that light has finally gotten here. And I do a whole presentation on the speed of light, which when you really think about it, and as an experiment, you go outside and we know that light from the moon takes about a second to get here. So every time you look at the moon, you're looking at what the moon looked like a second ago. Light from the sun takes 8 minutes. So every time you look at the sun, you're looking at what the sun looked like 8 minutes ago. If you really want an experiment, go outside and find Jupiter. You can't do it right now because it's not up, but you can find Saturn. Find Saturn, take a look at it and mark where it is. Then go outside 74 minutes later, and it's going to be over here. That's where it was when you looked at it over there. You're always looking into the past. Because of that, it gives us information because we know we're looking into the past, and that tells us in a way where we're going to be.
The
Yes.
web is launched, and so it's kind of a done deal in that regard, that you can't make innovations on something that's a million miles away. Is work being done on the next Hubble Webb, and then
Yes.
what?
Yes, I don't know the range. I think it's another visual scope. I might actually have to take a look at it. I did see the configuration. Looks very much like the Hubble does. That I can tell you. When the Hubble was launched, they actually started working. So it was a 10-year period to when the Hubble was launched. and Webb went up. So somebody's always innovating. So they can't make any changes to it, which is why they over-engineered it, and that's why everything in NASA, it gets over-engineered. And when we look at spirit opportunity, you can't fix them, so you over-engineer them so they can fix themselves. The only thing that the Webb does have, as I mentioned, is the fuel port, so that we can fill it up with fuel when it runs out in 10 years. And that's why I use the L2 point, because if it's very efficient on fuel, fuel last longer than 10 years, because we don't really need to change it that much, because it's a very stable orbit. But we're ready for that. You just can't change anything on it. But you can use the design for the next generation. Any other questions? Oh. Yes. It's got a solar panel. Yeah, it has a solar panel that runs, but you need fuel to run the reaction rockets to move it. So what happens is, as it's stable, it's a halo orbit. So it doesn't stay in one place, it actually goes like that. If you have to move it to do something else, you use a little bit of fuel that just kind of nudges it a little bit and nudges it back. But it also uses gyroscopes to help nudge it around. So it's just that fuel, the liquid fuel that runs the reaction rockets that you have to fill.